Welcome to another video in this big O notation series, and in this video we want to explore and visualize the big O of n raised to power 3, which is the cubic time complexity. So an algorithm with the big O of n raised to power 3 runtime increases cubically with the input size. So an algorithm with a time complexity of n raised to power 3 means that the number of operations required by the algorithm increases rapidly as the input size increases. So the growth rate will triple at every process. Before we explore the growth rate, if this is your first time coming to the YouTube channel, please ensure you subscribe and like, because we are going to cover a whole lot of use series and it will be a good idea that you should not miss any part of it. So what is the growth rate of n raised to power 3, the cubic time complexity? If you look at this input here, if we have an input of 2, the growth rate will be 2 multiplied by 2 multiplied by 2, which will give us a total growth rate of 8 for an input of what? 2. If we look at the input of 4, right, the growth rate will be 4 raised to power 3, and you can see it here. That is why we have what? N raised to power 3. So it's like n multiplied by n multiplied by what? N. So the growth rate of the input of 4 will give us the growth rate of what? 64. Same thing for the input of 8. It will give us what? 8 raised to power 3, and the total growth rate will be 512 at worst case scenario. So let's say, for example, right, we have an array of 4 elements and we want to pass it as an input to an algorithm that its time complexity is n raised to power 3. So what happened is, at the first index, every item is going to be visited 3x, but there is a fashion for it. So let's say, for example, right, at this index, we start with the first element. Then it will now go to the next loop, which is this one. And it will go to the next loop, which is the third one, which is this one. Then this, which is the third loop, will now move to the next one. And it will move to the next one, which is the one that has the value with 5. And it will move to the last one. So when the last array has been completed, when it has reached its endpoint, it will now go back to the second one and move to the second one. So at this second index, this last array will start to count again. It's going to visit this, it's going to visit this again, it's going to visit this, and it's going to visit this. So when this reach the endpoint, it will go back and move this to the next item. So at this index, it's going to visit this again, visit this, and visit this. This has gotten to the endpoint again. The same thing will apply to this one. It will move to the last item in this, and every item will be visited here. Every item will be visited. So now this has gotten to the endpoint, and this has also gotten to the endpoint. That is when this one will now move to 2, which is the first array. Will now move to index 1, rather, index 1. So at this index, the same process will start again. This will be visited, and when this has been visited, before this one will move to index 1, right? So this will be visited, this will be visited, this will be visited, and this one will be visited. It will now come back and move this one to index 1. When this has gotten to index 1, then it will go back here again. This will be visited, this will be visited, this will be visited, and this one will be visited. So since this one has reached its endpoint, it will go back and move to the next index. Then this process will repeat itself again, then until the endpoint. When the endpoint has been reached, it's going to move to this one, and this will be visited, this will be visited, this will be visited, and this will be visited. So the endpoint has been reached, and the endpoint of this one has been reached. That is when this one will now move to index 2. So at index 2, the same process will happen again, right? So this is like a breakdown of what is happening under the hood of an algorithm that has the time complexity of n raised to power 3. So this process will continue until this array reaches the endpoint. So with this demonstration I've given, let us look at a code example. I'm currently on my VS Code, and you can see I've created a file, a cubic time.py. And if you notice, right, in most cases, an algorithm with n raised to power 3, which is the cubic time, is O of n in 3 places. And you can see that here. Okay, this is 1, this is 1, this is another 1, and this one is another one. But not all cases, and I'm going to explain that. I'm going to give an example of that. Okay, so if we look at this algorithm, right? If you look at this algorithm, you will notice there is something similar in every O of n. And what is similar here is every loop is depending on the value of n, which is the length of the array. And the length of the array is the input size. Okay, so just as I have described in the last demonstration, this is exactly what is going on here. So let us look at the growth rate. So I'm going to save and run this code. Okay, so you can see the growth rate is what? 512. So we have how many elements here? I think we have 8 elements. This is what? 512. So now let me reduce this array to 4 items. So I'm going to comment out this one and run. You can see the growth rate is what? 64 at worst case scenario. Okay, and let me reduce this to 2 items. So I'm going to run this. You can see the growth rate is what? 8 at worst case scenario. The takeaway here is we have what? 3n, which is O of n. So, and in total, it's going to be n multiplied by n multiplied by n, which will give us a total what? N raised to power 3. And the reason why this is O of n, I explained that in the first video when I was demonstrating the O of n. So every loop here is depending on the input, which is the length of this array. So if this is 1, for example, right? If this is 1, for example, or let me even make it 2, or even 20, this is what? O of 1. And I'm going to prove that to you. Okay, so this is what? O of 1. So this algorithm will not be O of n cube again. So this algorithm is going to be what? O n raised to power 2. The reason for that is this part of this loop is not depending on the length of this array or the input size. So at worst case scenario, this is what? N raised to power 2. Okay, let me prove that to you. Okay, let me reverse it back and okay. So here is a little code snippet here. It's actually a big O checker built by someone else. So you can see there is no Python, but I'm going to give an example using JavaScript. I want you to know something here. You can see this is a loop, right? and this loop is depending on the length of the array. This is another loop, and this loop is depending on the length of the input array. There is another array, there's another array, right? So this one is also depending on the length of the array. So let me run this now. So I'm going to run this and get the big O. So if I scroll down, you can see this is what O n raised to power 3. We have here O of n, right? We have another one O of n, and we have another one O of n. So the reason for that is you can see this is what the O of n, and this one is the second one, and this is what the last one. Okay, all three loop, which is the O of n, they are actually depending on the input size. So the moment I change this now to 10, let me change this to 10 for example, and let me run. Now notice we now have what? O n raised to power 2. And you can see the last one I changed is now what? A constant time, which is this one. Is now a constant time. The reason for that is because this loop is not depending on the input size. All right. So guys, I hope this gives you a clear picture of how the big O of n raised to power 3 works. Now let us go to the big O cheat sheet, which is the big O complexity chart. So if you look at the performance of big O n raised to power 3 is not on this chart, but however, let me just draw it. So it's going to be somewhere around here. It's close to this one. So it's going to be somewhere around here, which is the big O of n raised to power 3. So you can see it is it is in a horrible state, right? It's not a good time complexity compared to what O of n. We even complain that this one is horrible, but it's kind of a little bit fair compared to the n raised to power 3. So guys, I hope you find this video helpful. On your own, you can actually go visit the bigocheatsheet.com to actually look at this example yourself and have more understanding. So guys, thank you very much for watching. If you have not subscribed, ensure you subscribe, ensure you like, and ensure you hit the notification button so that you will get updated on more videos. Thank you very much. I will see you in the next video.